Hi, I'm Keenan Casey for TestPlus.com. In this lesson, we'll be looking at support vector machines. Support vector machines are very popular right now, and a lot of people think they're the best off-the-shelf classifier. Support vector machines are nice because they have a very understandable geometric interpretation, but they're also very mathematically rigorous. We'll look at the basics of how SVMs operate. We'll talk about the soft margin version of an SVM and also the kernel trick. These are the important terms that we'll be using in this lesson. We'll have our input vector x and output classification y. Our training instances are the vector x combined with the output class y. The training set is the set of all training instances that we have input to output mappings for. We'll have n features, that's the number of columns in the data set, and we'll have m instances, which is the number of rows. As we begin, let me ask you this question. Which of these two separating lines is better? Consider option 1 on the left and option 2 on the right. Which of those two lines that separate the geeks from the non-geeks in this data set do you think is a better separating line? Well, I hope your intuition tells you that this one on the right is better because it seems further away from both sets of data. It seems like a better middle ground between the two classes. And this is the main idea behind support vector machines. We could imagine drawing this area around each separating line, and the bigger the area, the better the classification, because we seem to have a better hold on the actual underlying pattern between the two classes. In support vector terminology, we call this the margin, and bigger is definitely better when it comes to margin. So the first thing we need to consider with the SVM is this separating line. In 2 dimensions, as we've seen, it is in fact a line. Once we take it to 3 dimensions, this separating line is a plane, and in more than 3 dimensions, it's called a hyperplane. And let me show you a video of what this plane looks like in 3 dimensions. As you can see, there is a plane which separates the blue from the orange instances in this 3-dimensional data set. This hyperplane, or plane or line, is the decision boundary. So as we've already seen, the first element of the support vector machine is the separating hyperplane, which looks something like this. The next element is the margin. And the margin is the minimum distance to the closest instances to the separating hyperplane. So in this example, this is the margin, and you can see the distances shown with the yellow arrows. The support vectors are the instances that sit along this minimum margin area. So in this case, these 3 instances are the support vectors. We can imagine them supporting the margin, that is, supporting the hyperplane between the two classes. In fact, the decision function, that is the placement of the hyperplane, is fully specified by the support vectors. So if we can find those support vectors, then that's really all we need to know about this data set. We can ignore all the rest and remember what our support vectors are, and those will be the ones that define the decision. I want to give you some grounding on the basics of the math behind support vectors. This is pretty mathematical, more mathematical than the other lessons in this course. So I'm going to try to give you a quick overview of the important concepts, and you're welcome to dig into it on your own if you're interested. First, the hyperplane is defined in linear algebra using this form, where we have the weight matrix transposed times the x's, and we add this constant b to it. So this is the equation for the hyperplane. This is the mathematical definition of the margin, that is the distance between the decision boundary and the closest instances, the support vectors. We want to find the minimum margin, that is, what instances have a margin that is the smallest, because those are going to be our support vectors. And then we'd like to find a plane that maximizes that minimum margin. So for those instances that are closest to the decision boundary, we'd like to choose a line or a plane or a hyperplane that pushes that boundary as far away from them as possible. The problem then is we want to find the weight vector and the constant b such that the closest points have the largest margin. And this is the way of stating that mathematically. How do we solve this problem? Well, this is a really hard problem to solve. So using the magic of math, we can convert this problem to a constrained optimization problem using Lagrange multipliers. The result of that is this problem statement, where we want to find the maximum alphas to solve this equation subject to these constraints, where each alpha value is greater than or equal to 0 and the alpha y product is 0. If this equation looks difficult, it's because it is. Finding the alphas is the learning process for SVMs, and it's difficult computationally, mathematically. But once we have the alphas, we have our model. How then do we find alphas? Well, there are several advanced numerical techniques to solve this equation. One is quadratic programming, another one is called sequential minimal optimization, and both of them involve iterative, time-consuming numerical solving of these equations to find the best alphas. Typically, we use pre-written libraries to solve these sort of optimization problems. Once we have the alphas, how do we use an SVM? Well, the result is most of the alphas will be 0, and any alpha that is 0 means that the corresponding training instance is not a support vector. Only the support vectors will contribute to the weights, since all the non-support vectors have alphas of 0. First, we compute the weight vector, and we compute it as the product of alpha sub I, the output, and the input vector x. We only have to do this for the training instances that are support vectors, that is, that have an alpha greater than 0. Next, we solve for b, and we can do this using any support vector. So we just solve this equation for b using any support vector for x and y. And lastly, we can compute unknown quantities, that is, we can classify new instances by substituting them into this equation where we get the sign of w transpose x plus b. So for an SVM, doing classification is really quite simple computationally once we have the alphas, the weight vector, and the b value. The alphas are the really hard part of that. Next, let's consider an improvement to regular support vectors. Imagine we have a data set that looks like this, where it appears that we've got this outlier over here. Can we draw a separating line that can separate this data? We might be able to squeeze in this line right here, but you see, we've really pushed it over quite a bit. What if, instead, we drew this line and allowed the support vector machine to make an error? On the left, you see we have a very small margin, but it makes no misclassifications. On the right, we have a large margin that does make one error. Well, we call this version of an SVM on the left a hard margin. That is, it cannot make mistakes. On the right, we see a soft margin. Well, which one is best? Well, typically, we would rather have a model that can generalize, and the larger margin should generalize better. It has a greater tolerance to noise. Instead of fitting the noise, as we did on the left, we accept some misclassification. We're going to quantify this as the term C, and the value C is the misclassification penalty. Let's look at how we can do this with our support vector machine math. This version of an SVM is called a soft margin SVM. If we assume that the data is 100% linearly separable, then we have a hard margin. We have to get all the data separated. What if we relax this constraint? Well, it turns out all we have to do is change our constraints from this version on the left, the hard margin, to this soft margin where we put in a value C that is the maximum value for alphas. And when we solve this, we allow for some misclassification. If we have a very small value for C, then we have a soft margin SVM. That means we'll have more misclassifications, but we get a bigger margin, which is going to allow us to generalize better. If we have a large value of C, we call this a hard margin SVM. That means that we're going to have fewer misclassifications and a smaller margin, which may cause us to overfit much more often. The next version of an SVM I want us to consider is a kernelized SVM. A kernel is a mapping from one feature space to another. You can think about a kernel as a mapping that translates the data from a space that's hard to separate into one that's easy to separate with a line or a plane. Although the data may not be linearly separable in a lower dimension, by mapping it to a higher dimension, we can actually find a hyperplane that cleanly separates the two classes. And let me show you that. For this 2D data, you can see that there's no way to linearly separate it. However, if we envision it in 3D, there might just be a way. Let me show you this video to illustrate that. This data looks non-linearly separable until we view it in 3 dimensions. As you can see, as we rotate this in 3 dimensions, we now see that that data could be separated by a plane going across in this dimension. So this is just an illustration of how data points may be easier to separate in a higher dimensional space than they are in a low dimensional space. And this is the property that kernel takes advantage of in order to do better classification for machine learning methods, specifically SVMs. Let me show you one more example of how kernels map from one feature space to another, this in 2 dimensions. We can imagine here that these are our classes. This is our hyperplane, which looks very curvy, and that's because it's not curvy in the kernel space. In the kernel space, we see that there is this clean dividing line, this clean hyperplane that divides the black from the white dots. So kernels allow us to map from one feature space to another feature space and allow us to more easily separate the data. What kind of functions are used as kernels? There are several that are common. Wanted to mention them here. First, the radial basis function, which is pictured here, is often used. Secondly, the sigmoid function, which is used in neural networks as the activation function. You can also use a polynomial kernel, or as we saw in the original version, just a linear kernel. If we use a kernelized SVM, how does that change the classification process? Well, it really doesn't change it that much. We first have to solve for B using a support vector. We can do it using this equation that involves alphas, and this is our kernel that maps between 2 instances. Secondly, we compute the unknown input x question mark using our alpha vector and the support vectors. We do so using this equation, which just uses our support vectors and our kernel function to compute the new classification. So why should we use a kernel where there are several strengths and really just a few weaknesses? The kernel allows us to do nonlinear classification, which generally provides better performance. The kernel is a complex model, but it still generalizes well. And lastly, we have several different choices for kernels so we can adapt and optimize to get the best performance for our data. In terms of weaknesses, we still have to choose the kernel and tweak the parameters to get the best performance, and that's a pain. Also, there is the computational overhead of going to that higher dimensional space. We have to compute that kernel function many times. Let's sum up SVMs and look at their strengths and weaknesses as well. The support vector machine is accurate. It has very good generalization properties, especially for the binary classification task. You can see this is what they were designed for. That separating hyperplane naturally lends itself to separating into 2 classes. Once we have our model created, using an SVM is quite cheap computationally, and it provides some interpretable results because we have those support vectors which really encapsulate the model and say, these are the instances that matter the most. What are the weaknesses of SVMs? Well, their training is computationally expensive. It takes a long time for a computer to solve, especially with large data sets. We may have to choose the value C for our soft margin SVMs and the kernel and its parameters. Thirdly, support vector machines don't support regression and multi-class classification as naturally as some other methods. And lastly, they may be sensitive to noise in some situations. If we have a relatively small number of mislabeled examples, this can really hurt our performance. What does an SVM look like in terms of its representation, evaluation, and optimization? The representation is really just this set of support vectors, our kernel and its parameters, and the value C if we're using a kernel and or a soft margin SVM. The SVM is summed up through this representation of our alphas and our kernel, our B, and pushing that through the sign function. How do we evaluate the SVM? Typically, since it's a classifier, we'll consider its classification accuracy, number of correctly classified over the total instances. And lastly, how do we optimize an SVM? As we've seen, there are several methods to find alphas and find the best alphas. Quadratic programming and the SMO are 2 methods for doing that. Furthermore, we may need to find the best values for C, the best kernel, and the best kernel parameters like sigma for a radial basis function. In this lesson, we've looked at the support vector machine, which is a very popular, well-performing classifier. It's a form of supervised learning. I'm Keenan Casey for Tuts Plus. Thank you for watching.